Okay, entropy and disorder. So the word entropy seems to go along with enthalpy and with energy, and they're all part of these thermodynamic things. They all deal with kilojoules or joules in some way. All right, and a little bit of history behind this term entropy. This whole idea of thermodynamics comes out of the building and drive to make more efficient of a steam engine, and we're talking late 1600s. So the first steam engine is built. You know, somebody builds a tank that you have a fire underneath, and you boil water, and the water becomes steam, and that steam is pushed into a cylinder with a piston, and that steam pushes the piston, and that piston then is mechanically connected to some wheels, and that steam engine is pushed forward by the steam itself. All right? And if we want to talk about industrial revolution and history, blah, 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 you can take a history course. But in terms of science, right, the question was, how is that heat energy being turned into work or moving energy, all right, or into kinetic energy, right? So this was the first kind of time when heat was on purpose turned into work or some kind of force that can move through a distance. So questions were starting to arise. How much work could you get out of a little bit of heat? Is there a certain maximum amount of work? Is there a maximum efficiency? And that has everything to do with even our modern day engines, right? We now use gasoline instead of heating steam, and we put the gasoline and the oxygen in a cylinder, and you put a spark in there, it lights on fire, it creates hot gases, which then creates heat, which then try to expand, and then pushes that piston down, and then it runs through the transmission, and your car goes down the road. So the question is, how efficient could it become, and what's kind of driving all of this? And in actual fact, there was an idea, this entropy idea actually came before the idea of enthalpy, energy found in a chemical reaction. This entropy idea was kind of conceived before the enthalpy idea, and it involved kind of a degradation of heat energy. All right, it was very well known that you could have a lot of heat concentrated in one area, like the fire, and then how that heat eventually becomes spread out, and it becomes very cool. It kind of spreads itself out, and the heat energy is the same amount. It's just instead of it being concentrated, it's kind of spread out into a lower temperature entity that's covering more area. And this degradation of heat energy was well known at the time to represent the fact that you couldn't use that heat energy anymore to, say, run your steam engine, because if the temperature was too low, you couldn't boil the water, and then you couldn't run your steam engine anymore. So the heat that you had at the beginning was concentrated and useful, but the heat that left the steam engine at the end was spread out and not useful. And so there was something about the usefulness of heat energy that could then either do work if it was concentrated, or not do work if it was spread out too much. And this degradation of heat energy was given a name. It was called entropy, all right? So heat could be in a useful concentrated form or a less useful spread out form, all right? Now, in the end, we now can associate, after hundreds of years and looking back on what the scientists had discovered, we can look at entropy in two different ways. One way, we can now say that this entropy is actually a quantity of useful work, pushes, forces, that it can apply onto something, all right? So if you've got a gas that's hot and it's compressed, and you let that compressed gas push on a piston, it can actually move that piston, all right, and do some work. So the entropy in there is kind of a measure of how much pushing, actual physical pushing, that a gas or some fluid can do, all right? So that's one interpretation. It's actually the real amount of work, a physical push that a substance can do because of its high energy content and do some work. All right, that's one interpretation. There was a second interpretation that came about in the mid-1800s. And this was a mathematical interpretation. And this was determined by a guy by the name of Maxwell. He's also very important significantly in that he kind of theoretically explained light as a wave. Has nothing to do with entropy, but he was a very mathematical guy. Another guy by the name of Boltzmann, he was working with. What Maxwell and Boltzmann did was they decided to sit down and mathematically explain the behavior of individual particles, all right? Now, let's not worry about whether they were molecules or atoms or, some kind of, mixture or whatever. He was just worried about each particle. Let's imagine that we can think of a gas, which is made of billions of particles, as a single particle, and let's give that particle some speed. We'll call it speed v, and let's give it a mass, and we'll call it mass m, and we'll have it travel through space, and we'll have it run up against a barrier like a wall, and then we'll do some mathematics, and we'll calculate what force it can apply, and then we will now multiply that by millions of particles, and we'll start doing lots of fancy calculus and math, and in the end, they were able to successfully kind of model what a mixture of particles would be mathematically. So essentially explain all the important properties of that gas, pressure, temperature, volume, et cetera, mathematically. Now, once they started to look at the mathematics, they realized that this property of entropy, it can be thought of how much work or pushing force it can do on a substance, can also be thought of the disorder of the particles in a substance. And so it mathematically was being presented that another way of looking at entropy was not in terms of how much work it can do, because that's what it is, that we can also determine that, but in terms of how disordered the system is. If you've got a gas that is compressed in a little space, all right, at a certain temperature, then the particles are confined. We would say that it's an ordered system. We've confined all the particles in a little area. If you were to then let that gas expand out into, say, a room or into another container, then those particles are now able to move around and be far more chaotic and disordered than they were when they were confined. And this spreading of the particles increases the disorder. So we now know entropy also to be a measure of disorder of a system, okay? So an example, if I have a piece of ice and all of the water molecules are nicely ordered in a lattice structure, rows of water molecules in a nice solid structure, we would say that that is very ordered. Its entropy would be low. If we then melt it and have the particles move freely within a container in the liquid form, then those particles are free to move from one place to another. That is a higher degree of disorder. Those particles can now move freely, and we say the entropy has increased. All right? Okay? So entropy nowadays can be thought of as a measurement of disorder. So entropy has all kinds of different interpretations depending on what your field is. If you are a mechanical engineer and you are trying to build a better engine, then your interpretation of entropy is how much work that particular thing can do, how much of a push it can do on a piston. If you're a chemist and you want to study a chemical system, then we're worried about how disordered the chemical system is. Is it highly chaotic? Is it in the gas phase, or is it in the liquid phase, or is it in the solid phase, all right? Are there many little particles, or is there one big ordered molecule, right? And so entropy has this idea of being a measurement of order, okay? And that's the way we need to interpret it. We need to interpret it in terms of order. It is important to keep in mind that it's still a measurement of how much work it can do, but we want to think in terms of order. Okay, so let's define entropy. Entropy is a measure of the degree of randomness or disorder in a microscopic system. And here's a classic little comic, an interpretation of entropy. And here we've got Department of Entropy, and look at this guy, he's got a broken window, and the trash can is on the floor, and there's the board missing here, and he's got an old calendar that's like many years old, and the door's falling off the hinges, and there's a crack in the ceiling, etc., etc. Ha ha ha! It's chaotic. There's lots of disorder, and it is the Department of Entropy. In actual fact, you cannot really talk about the entropy of a macroscopic system in the same way that we talk about entropy of a chemical system. But people do that, right? You know, I'm sure Sheldon has made reference at some point in time of some kind of swirling chaos of entropy that he doesn't like, because Sheldon likes everything in order, right? And we always, we always make the joke as chemistry teachers when we're teaching about entropy to talk about how, your bedroom might be in total chaos and has a high degree of entropy, all right? But in actual fact, you can't really talk about that, because if your bedroom is in order, right, and then your bedroom is kind of messed up, all of the little microscopic particles that make up the contents of your bedroom are still in the same essential order if they're in the same state. It's just that it's messy. So you really haven't changed the entropy of the substances in your bedroom. You've just got a messy bedroom, right? And we've sometimes, as chemists, make the joke, you can say that you've got, a bedroom high in entropy. It's very disordered. But in reality, all of the particles in your bedroom are still in the same entropy state as they were. They're just messed up a little bit. So that really doesn't really count. All right. Before we talk a little bit more about chemistry and entropy, let me just talk about one more physical interpretation of entropy that is kind of interesting just on a theoretical kind of discussion. There's a law that states that the entropy of the universe is always increasing, all right? Tomorrow we're going to learn about what makes a spontaneous chemical reaction. Why do some chemical reactions go, and why do some chemical reactions don't, some chemical reactions don't happen, right? Like if I have hydrogen and oxygen and I put some fire to it, boom, I can make it turn into water. But if I have that cup of water sitting there on the desk, it doesn't just naturally turn into hydrogen and oxygen. Some reactions happen and some don't. And one of the laws of nature states that during a change of some sort, whether it's chemical or physical or nuclear, the entropy always of the universe increases a little bit. So you always have a little increase in entropy. And that's kind of how the universe drives. Things naturally degrade and increase in entropy, all right? And it's some scientists even believe that our perception of time traveling from the past to some point just in front of us in the future is driven by this increase in entropy, because you only see certain things happen. You never see the reverse. If you were to have, say, some eggs out on the counter, you're going to make some breakfast, right? And you leave and you come back, and for some reason an egg has fallen off the table and is broken on the floor. You can predict what happened in the past. It's kind of a silly thing to say, but you can make a conclusion that, one of the eggs fell off of the table and landed on the floor. If you were to leave the room again and come back, and now the floor be perfectly clean with that egg sitting back on the table, you'd be really freaked out, because that doesn't happen in our universe. You never have a chaotic, disordered, broken egg reorder itself spontaneously and end up back on the table. Those things don't happen. It's technically a non-spontaneous situation. So what we perceive as a spontaneous traverse through time, going from things that are ordered, like a shiny new car, you know, you may have just got your final license and your parents bought you a car, because that happens all the time, right? So they bought you a nice red, what kind of car would you like? You'd have no idea. She doesn't want a car. We'll go with a Mustang. I'm not a fan of Mustangs, but anyway. Nice red Mustang. After 4 or 5 years, automatically, it's not going to be as shiny. You might have a little bit of rust forming on the bottom. 10 years, you'll have lots of rust. You will never have that nice shiny red car that you first got when you got your license spontaneously revert back to its original form. That doesn't mean you can't fix it up. You could put some energy into it, but it would never spontaneously revert back to that original form. So some scientists believe that our perception of time is simply kind of determined by this step towards more chaotic systems. Some scientists believe that in actual fact, time is like a distance measurement, and you can have a point in space here and a point in space there, and you can have a point in time, say 2015, and a point in time, say 2012, and they all exist simultaneously, except we perceive that we're passing through time, even though all time points exist as equally as all position points exist in this room. It's just that we can only perceive time passing us because of entropy. It's an interesting theory. The reason we perceive, and here now I'm off on a tangent, talk about a math tangent, now I'm really off on a tangent. If you think about it, whenever you make, I shouldn't be videotaping this because this is my verge of Mr. Sanders is a little crazy here, but that's okay. If you think about it, the way our minds record a memory event, all right? So you see something. Mr. Sanders is up here, he's ranting, he's losing it, and you hear it, and you see it, and you sense it. In your brain, now this is where I'm not very good at because the biology part, some neurochemical reaction takes place, and it imprints that moment in your brain, okay? Now, after the moment happens, right after the moment happens, those chemicals that are formed in your brain that are the memory are beginning to degrade. Other chemical reactions are taking place. They may start to break down, and the memory of that moment begins to maybe fragment a little bit, and in a week from now you might say, do you remember that rant Mr. Sanders went on? You might not even remember what the rant was about, whether it was about time or whether it was about entropy, but you remember a rant. So what's happening then is that memory is degrading in time due to entropy. All right, it's becoming more chaotic in your brain because of entropy. Okay? Now, whether we exist at point B in the future or point A in what we call the past, if even though all of those particular points can exist, the point that is now is simply defined by the freshest memory chemicals in your mind. The points that are the past are degraded chemicals, and the points that are in the future will have new fresh chemicals made at that point in time, but it doesn't really matter which point in time you're in. They all equally exist. There's just continuing chemical reactions that degrade. Oh, you can go online and find some really wild stuff. It's pretty cool. And it's all backed up by some pretty good science. Anyway, all right. Mr. Sanders has lost it. It's true. I've talked with Petrus about this when he says, don't tell people that. It's true. I've read it. It's good stuff. Anyway, all right. Let's talk about some chemistry. Oh, that's fun. Okay. So, It's changes in entropy that only count. Because that's what determines time. Oh, sorry. Now an entropy has an energy value because, again, remember, it's kind of the amount of work that a chemical, well, not necessarily a chemical system, a chemical or physical system can do. So it has an energy value. With enthalpy, we couldn't know what the absolute enthalpy was because we couldn't determine what that lowest energy was. Heisenberg uncertainty principle prevents us from knowing what the least amount of energy is, et cetera, et cetera. In terms of entropy, you can know the absolute entropy of a substance. Because all you have to do is define the absolutely ordered solid to be zero, perfect order. And so for our spontaneous chemical reactions or not, but that's what we eventually want to look at, we want to look at the change in entropy. How is the entropy of a system changing? So the change in entropy can have a positive or a negative value. Entropy itself cannot have a negative value. You can't have something more ordered than absolutely perfect order. Zero entropy would be perfect order. In terms of a chemical system, that would be a solid of a substance. Let's pick a metal, it makes no difference. Iron, that has all of the iron atoms in absolute perfect rows, nothing out of alignment, nothing out of its place, perfect zero entropy. But if we're talking about the change in entropy, let's say I took that particular perfect crystal of iron and I heated it and caused some of them to leave, then I would have increased the disorder and I would have a positive entropy change. I've caused it to become more disordered. And if I could somehow put the particles all back into their order, then I've got a negative entropy change and I've made things become more ordered. Okay? So a change in entropy is a measurement of whether we're going from order to disorder or the other way around. Okay? All right. Let's talk about some qualitative ways in which we can have increasing entropy in a chemical system. And you do not need to draw pictures of these things. They're just kind of illustrating how it's more disordered. But if I have a gas in a certain volume and I let it expand out into a larger volume, that's an increase in entropy. That's essentially like pushing the piston. It's doing some work. We can think of it in terms of chaos or disorder. Here we've got a gas. They're closer together. Their positions are more defined in space. We let them into the other space, and the positions are now a little less defined. They're in a greater space. My example of that is would be like teaching a kindergarten class. I couldn't do it. In the classroom, there'd be way too much entropy to begin with because there'd be kids all over the place. But then when you let them out for recess or something, you open the door, boom, there'd be kindergartners everywhere, all over the place. And if you leave a gate open at the far end of the playground, then you got kindergartners out on the street wandering all over the place. Just chaos everywhere. Again, more chaos, increase in entropy. So volume of a gaseous system increases. That's an increase in entropy. Entropy is also related to temperature. Increase the temperature of a system, and the particles are vibrating more. They may vibrate out of alignment. That's less ordered. Do we want an analogy for that? Give the kindergartners chocolate bars just before you let them out for recess. It would increase their temperature. I don't know. Anyway, they'd be bouncing all over the place. So increase the temperature, and that is also an increase in entropy. Physical state change. Solids have low entropy, liquids have moderate entropy, and gases have high entropy. My analogy for that, well, gases, kindergartners. Low entropy, my classroom, with all of you sitting nicely in your rows, representing a nice behaving solid. Thank you. Medium entropy, I don't know, most phys ed teachers, maybe an art class, people wandering around, getting things. No, I don't know. No wandering in art? Okay, phys ed. We'll go with phys ed. You know, kind of moving around, doing stuff. Anyway. Too much chaos. Yeah, there's a little bit of entropy in my labs. It makes me nervous. I don't like it. Anyway. All right. So physical state change, obviously. Nicely ordered, lots of movement, disorder. Okay. Dissolving of a solid. And this is just a little video. It's not going to run because of the new PowerPoint version we've got. I don't have the little plug-in that runs my little animations. You've seen that one in the past, last year, before we had the new PowerPoint. It's got a solid, and it's got the water molecules, and it takes the particles away. It spreads the ions out. So the ions that used to be in a nice solid are now spread out in an aqueous form, and that is an increase in entropy. When a gas dissolves, though, it's the opposite, right? Because a gas is already very chaotic, and if you dissolve a gas into a liquid, you force it into the volume of the liquid by dissolving it. You've actually, ordered it. You've put it into a smaller space there, and it actually is a decrease in entropy. It actually makes it more ordered. All right? That kind of makes sense. So the solid is already of low entropy, and you're dissolving it in a liquid, which has got more chaos to it. And the gas is of higher entropy than a liquid, and if you force it into a dissolved state, then you're forcing it into that area of the liquid. So that is actually a decrease. Okay. Now, what if we're talking about chemical reactions? The list we just did, we're talking about physical changes, right? We haven't really changed the chemicals in all of those examples that we talked about, changing the volume and changing the temperature and the physical state and dissolving. What if we're talking about a chemical reaction? So during a chemical change, we've got, right, new product molecules. And really, it has to do with the entropy of the reactant molecules compared to the entropy of the product molecules. Fewer moles of reactant molecules that produce a greater number of moles of products that are in the same state. That is an increase in entropy. Now, looking at this example, there are two NH3 particles. Two. And we don't care the fact that they're the same type. There's two molecules there. In the products, we've got one nitrogen molecule and three hydrogen molecules. So in the end, our two molecules become four molecules. That's more disordered. That's an increase in entropy. Now, they've got to be in the same state. As soon as you have one turn into a solid or a liquid, that also has an entropy effect, and then we'd have to take that into account separately. But if they're all in the same state, 2 becomes 4, that's an increase in entropy, more chaotic. And again, keep in mind, they're moving around, they're bouncing around because there's heat involved, et cetera, et cetera. They're in the gaseous state. So 2 particles moving around versus 4 particles moving around in the same reaction vessel, more chaotic. Oh, that's good. Yes, we're going to draw them all out. No, I'm not doing that. We don't need that. You don't need to draw all these molecules, but you can write the chemical reaction. A complex molecule, big biological molecules actually have order. All of the atoms are locked into the positions of these larger molecules. In this case, I've got a glucose molecule. And so this is an ordered state. Life shouldn't exist if entropy was the only thing governing the universe. And it isn't. There's a secondary effect I got to teach you about tomorrow. But if molecules naturally tend towards chaos and naturally will undergo chemical reactions that will cause more entropy, then all of our big biological molecules in our bodies at some point in time should have either oxidized or perhaps reacted with something else and should have broken down into more simpler molecules if entropy was the only thing that was governing the universe. There's a secondary effect. So this is an increase in entropy, the breaking down of that molecule. One ordered molecule with 6 gaseous ones to produce 12 gaseous molecules, that's more chaotic than that. Okay? If you want an analogy, that would be like tying your kindergartners together if you were going on a little field trip and then somehow they get loose and they're gone, right? You can't contain them anymore, right? And no, I do not promote tying kindergartners together, just for the record. Duct tape, maybe. Solids becoming liquids or gases. That's a representation of that physical state change. So here we've got sodium bicarbonate, solid, breaking down to sodium carbonate solid, but also some gas and some liquid. 2 particles becoming 3 particles. 2 solid particles becoming 1 solid with a gas and a liquid. More chaotic, less chaotic. That's an increase in entropy. The entropy is going up. All right. So don't necessarily write these down. Actually, don't write them down. I've got some example problems for you to do. This is really just to take a look for check for understanding. So here I've got delta S greater than 0 or delta S less than 0. You know what? I'm not a fan of the greater than or less than 0 symbols. I often like to put it as maybe the delta S, if it's greater than 0, is positive. In other words, it's a positive number. Or the delta S less than 0 is negative. All right? So delta S is positive or the delta S is negative. Delta S is positive. Just as a check for understanding, am I heading towards disorder or order if it's positive? It's disorder. So this is disorder, all right? And if it's negative, it's order, right? Where it's becoming more orderly. So if we're going from carbon dioxide solid to carbon dioxide gas, what did the entropy do? Is the change in entropy positive or negative? It's positive. That's a positive change. So the delta S is positive. It's becoming more disordered. All right? Does that make sense? Okay. How about that one? Is the delta S positive or negative for this one? Positive or negative? 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 Why is it negative? Sorry? Less moles of gas. 2 molecules becoming 1 molecule. That's more orderly. So the delta S is negative. All right? Okay. How about that one? What's the delta S doing there? Yep. Positive. And why is that? More moles, and the solid is becoming gas particles. It's more chaotic. So delta S is positive. And last one there. What is happening there? What's happening to the entropy? Yep. Negative. Delta S is negative. Why is that? 2 to 1, yes, but there's a bigger effect there. It's not just the 2 to 1 on that one, yep. Yeah, from the aqueous ions, they're becoming solid. So the aqueous ions had the ability to move around in the water, that's great, and now they're locked into a solid lattice structure as the solid that is more ordered. I would say the aqueous becoming solid is a greater effect than the 2 becoming 1 there, all right? Okay. There is a way to actually calculate the delta S. Now, this is the old equation that I used to use that have the products at the end. But if we were to rearrange this, it would become negative the sum of the entropy of the reactants plus the sum of the entropy of the products, which makes it look exactly the same as our enthalpy equation that we used yesterday. And I haven't adjusted this PowerPoint, so if you're wanting to memorize one equation, I like the reactants plus the products, negative reactants plus the products, because it just means you just have to work underneath whatever your chemical reaction is. So now going back to our thermodynamic table, you'll notice that the second column is entropy, just S. And that's the entropy value for those particular chemicals. Couple of major differences to point out. Check the entropy for graphite, C solid graphite. What's the value? Yep. 5.7. What's the entropy, what's the enthalpy of formation for carbon solid graphite? 0. Remember all of those elements in the standard state when we talked about enthalpy of formation had an enthalpy of formation of 0? The entropy is not 0. So be careful with that. We can't just discount those elements in their standard states now when we do problems with this. Also, look at the unit for entropy. What's the unit for entropy at the top there? Exponent -1 is the same as per. So the other one is kilojoules per mole. So how would we pronounce that one? Yep. It's actually not a kilo. It's actually a Kelvin. There's a temperature in there. So it's joules per Kelvin per mole. So there's a Kelvin in there as well. And notice it's joules. It's not kilojoules, which means when we start working with both the entropy and the enthalpy, we're going to have some unit changes. Let's do some calculations to find the entropy changes. Just put e.g., determine the delta S, and interpret the results. Let's just Just put EG and put number 1 and we'll calculate it. Don't worry about writing determine the delta S. That's what we're doing, obviously. We just wrote the equation down. We already made the estimation on this. We estimated that the delta S should be which sign? Actually, this is flipped from that. What should it be? It should be positive. Let's check it out. So now we're going to use our data to calculate it. Delta S equals, just like yesterday, negative, brackets, the number of moles, 1. I now need an entropy value for N2O4 gas. 9.2? Nope. 4.3, and I don't think I can erase. What is it? 304.3. Oh, I can turn that into 0. 304.3. 304.3. And that's it there, so we can close that up, plus 2 NO2 gas. Yep. 240.1, 240.1. Notice they're all positive. S's are all, they can only be positive. The delta S can be negative or positive, but S's are all positive. So this becomes negative 304.3 plus, and what's that, 480.2? 480.2. And put that together, and what do we got? No calculator? Oh. Oh, it's a very sensitive calculator. What do we have for a number? 175.9 joules per Kelvin mole. That Kelvin in there is because there's a temperature effect. You increase the temperature, you'll change that entropy. We predicted an increase in entropy, positive. Yep, that was a good prediction. Very similar to what we did yesterday. Let's do one more, just to make sure. Oh, I see a PCl2, but I don't see a PCl3 and 5. Or no, I'm looking at PB. All right, where are we looking at? Phosphorus. PCl3. I don't have the PCl5. Am I missing it, or can we see it? We don't have it. I'm going to look it up online so that you guys can finish the question. So you can start writing your numbers down. I will find PCl5. It looks, I got numbers all over the place here. Gas, 364.5. What is it for PCl3? 311. I think that's got to be a good number. So I have here for entropy for PCl5, 364.5. 64.5 joules per Kelvin mole. Okay. So you guys are probably now way ahead of me here. Delta S negative 1. What is the PCl3? 311.8. 311.8 plus 1 Cl2. 223.1. Put that all together, negative, plus, and then there's just one of these guys, 364.5. 364.5. And that's that. We didn't even make a prediction. What's the prediction going to be? Negative 2 becoming 1, it's becoming more ordered. Negative, and somebody have that number in there? Yeah, what you got? 534. I got the 534, and then I lost the decimal. 9? 534.9 plus 364.5. And we got a total? Yeah, go ahead. Negative 170.4 joules per Kelvin mole. All right, or negative 1 Kelvin, negative 1 mole. It just means it's on the bottom of a fraction, right? Calculating the change in entropy is very straightforward. It is just like what we did with the change in enthalpy yesterday, except we just use the other column and we've got some different units. And I think we've got to be pretty close to done. And like I said, this is not in the textbook, so I had to make a worksheet up, and I'll hand that worksheet out. So we will